Welcome. So let's start now. I'm not going to waste the class time waiting. Here I'm going to cover all the topics that are going to be on that test, that most of which are on the homework that you just submitted. The first one is the comparison test. And I didn't have many people answering properly the questions. You need to provide all the details that are given in class for this, because any of them that is missing means you have a wrong answer. You don't get to choose what to do and what not to do in the answer to the problem, because those are the steps that are provided. That's the strict minimum that you need for the answer to be correct. So the comparison test, it's you have a series, sum of a n from 1 to infinity, and if you build if you build bn that is larger than or equal to an, and sum of bn converges, then sum of an converges. It is an that is less than bn, not the series that is less than bn. And it's the sum of bn's that converges, not bn that converges. And two, if you can put bn below an and sum of bn's diverges, then sum of an's diverges. There is no third option. Those are the two options. And so you had a problem, sum k from 1 to infinity, sine of 2 over k divided by k to the power 4. And if you are using the comparison test to answer this question, you can report what is AK. Here, that's sine of 2 over k divided by k to the power 4. Now, your BK that you can find, depending on what you know about these functions, you could say sine of 2 over k is always less than 1. It's positive as well. So, yeah, first of all, important to have that AK is positive and AK is less than or equal to 1 over k to the power 4, which you define as BK, and this is because sine of 2 over k is less than 1 and it's positive. Now you have a BK and you show that AK is less than BK. Why am I putting BK on top? That means I'm leading towards the first option because I want to show that it's convergent. If I wanted to show that it's divergent, then I would try to put something below, not on top. And now, important to show that this thing converges. It's not just one statement you're writing there. Sum k from 1 to infinity. This thing converges. And you need to prove that it converges. Why does it converge? It converges as P-series. Not all of them are going to be P-series. This converges as P-series with P equal 4 larger than 1. Now you've shown that the sum of BK's converges. BK is larger than AK. The AKs are positive. Therefore, by the comparison test, sum of sine 2 over k to the power 4 converges. Any questions? It could have a second example. Sum k from 1 to infinity 3 over 2k squared minus square root of k now stuck here plus. Now in this case, you have 2k squared and then you have square root of k. This thing is larger than that. Therefore, the leading is that one. And luckily, so AK in this case is equal to 3 over 2k squared plus square root of k. This is positive and it is important to have that. And because 2k squared is larger than the root k you have here, and 1 over k squared, if I take the sum, that would be like a p series with p equal to converges, then I'm be thinking that this thing converges, and therefore I need to build a series that is larger than this. And so here, the good thing to see is that we can drop square root of k. If we drop square root of k here, we get a number that is larger, so the inverse, sorry, if we drop square root of k, we get a number that is smaller, so the inverse is larger. Therefore, this is true. And you are going to take that as bk, and then go to another line to show that the sum of bk's converges, because that's what you want to show. K from 1 to infinity, 3 over 2k squared, and this thing is 3/2 sum k from 1 to infinity, 1 over k squared. And this is a p-series, so that converges as p-series with p equals 2 larger than 1. So by the comparison test, the sum k from 1 to infinity, 3 over 2k squared plus root k converges. If on the other side I had k to the power 2/3 minus square root of k, then we still think here, which of these two things is larger? K to the power 2/3 is larger than square root of k. That makes it that this number here is positive, first of all. Moreover, it will behave like something with 1 over k to the power 2/3. And then that is a p-series there with p less than 1. So you're thinking that it is divergent. And if you're thinking it's divergent and you need to use a comparison test, then you need to put a sequence below that. So you gotta get AK in this case, that's 3 over 4k to the 2/3 minus square root of k. And you need to put this function above, because you are thinking it diverges. And what is smaller than 3 over 4k to the 2/3 minus root k? Oh, and that'll be easily found here as 3 over 4k to the power 2/3, because when you subtract root k, you are making the denominator larger, so you are making the denominator smaller, so you're getting a larger fraction when you have a smaller denominator. Therefore, this inequality is true. And so you are going to call this guy bk, and then tell us that you get that AK is positive and this BK is positive as well. The BK that you found is positive. Because if you find a negative BK, then it's useless. And now we are going to look into sum k from 1 to infinity of BK, which in this case is 3 over 4 k to the 2/3. That is 3/4 sum k from 1 to infinity, 1 over k to the 2/3. And this is a divergent P series. Would P equals 2/3, which is less than 1. Therefore, by the comparison test, the series, the initial series diverges. That series. That's how it's used. Any questions? And it doesn't always have to be P series, you know. If we have a series like this and we ask you to use a comparison test, what do you think? Is this series going to converge or not? And what we do?
Do you have to take out one of the functions in the denominator?
That's correct. And what's the feeling first? Do we want to show that it converges or that it diverges? Because that's the first decision you need to make.
I think we should show that it converges.
Okay. And so we want to show that it converges. That's the first thing you're feeling. And that actually dictates already what you want to do. Why do you feel it converges?
Because I see more, I see bigger things in the denominator than the numerator.
No, that's not enough to decide that. It's something clearly that you should see there that actually tells you already what your BK is going to be. If you're going there, you are seeing 2 and 3. 2 to the power k and 3 to the power k, that is 2/3 to the power k. That is a number that is less than 1 raised to the power k. So you're thinking geometric series and you're seeing that thing converge. That's the thing you have there, right there. And you should see that in the functions that you have here. Here we were seeing P series. Here with powers, we are seeing a geometric series. And the guess would be if we drop 2, then we will get 2/3 to the power k. And that's a converging series. And that's why we're going to do that. So here, you're going to have AK is less than or equal 2 to the k over 3 to the k. If we drop 2, we get a larger, which is 2/3 to the power k. And we call this BK. And then we go sum of 2/3 to the power k, k from 1 to infinity, and this converges. Geometric series. With absolute value of r equals 2/3 less than 1. Thus, by the comparison test, sum of 2 to the k over 2 to the k plus 3 to the k converges. That's it. Now that was comparison test. Again, those are the rules. If you have sum and you feel it converges, then you put a series, you put a sequence on top, you show that the series that is formed with that sequence converges, then you conclude that the original series converges. If you're feeling that your series diverges, then you put a sequence below the generating sequence and you show that the sum of that sequence diverges, then you conclude that your original series diverges. That's what you call the comparison test. Now, what is the limit comparison test about? That's the second part. And the work is completely different than from the other one. And so you have sum of ANs, 1, and you gotta find a BN and get limit of AN over BN. That's part of the solution. You need to find this limit. And based on that limit, you're going to decide. So if you give me an answer with limit comparison test where you don't have such a limit, you're not doing anything. Because that's where the limit comparison test comes from. That's where the name comes from. You need to have that limit. Now, based on that limit, you got to decide whether the series converges or diverges. If you don't have that limit, I don't know how you're deciding. And after taking that limit, you got 1. If L is not infinity and L is not 0, then sum of AN and sum of BN converge or diverge simultaneously. That's the rule. If L is 0, that would mean that Bn is too large compared to An, and therefore if sum of An diverges, that would imply that sum of Bn diverges. If L is infinity, then that would mean that An is too large compared to Bn. Therefore, again, I said AN is too large compared to BN. Therefore, sum of AN then start sum of BN diverges implies sum of AN diverges. And then this one here is also equivalent to sum of BN converges implies sum of AN converges. So those are the three rules that you have in limit comparison test. And they are all based on that limit. So if you don't even have that limit, I don't know how you're choosing any of the three to apply. Now let's get an example, same as what we did earlier, sum, okay, from 1 to infinity, 3 over 4 k to the power 2/3 minus square root of k. That same question that we answered using the comparison test. In this case, we can also answer this question using the limit comparison test. And so here, when we have a question of this form with polynomials, we think of bk. ak here is 3 over 4 k to the 2/3 minus root k. And then we think of how this ak behaves as k goes to infinity by taking the largest powers of k for the top and the bottom. Here it's 3 over that. So we would be thinking bk as 1 over k to the 2/3. And you're gonna give me limit as k goes to infinity of ak over bk. That's limit as k goes to infinity of 3 over 4k to the 2/3 minus root k over 1 over k to the 2/3. You're gonna find that limit. That is k to the 2/3, 3k to the 2/3 divided by 4k to the 2/3 minus square root of k. And for this limit, it's kind of powers of k, so you're going to take the ratio of the highest powers of k for the top and the bottom. So that is 3k to the 2/3 over 4k to the 2/3, and it gives you 3/4. And so that's 3/4. It's not 0 and it's not infinity. Therefore, sum of 3k to the 2/3 minus root k and sum of 1 over k to the 2/3 converge or diverge simultaneously. So that's what the theorem would tell you. For this case, they converge or diverge simultaneously. You're up to that point, and now you would decide whether they both converge or they both diverge based on what you will decide for this series. Does this series converge or does it diverge? And then you will conclude for the other one. Good. Sum of 1 over k to the 2/3. Does this diverge or converge?
It diverges.
Diverges. That's P series. It P equal 2/3 less than 1. And anytime you're saying something diverges or converges, you need to provide evidence for that. Thus, or therefore, sum of 3 over 4 k to the 2/3 minus 3k diverges. So you can show it any using limit comparison test or comparison test on this question, you will reach the same conclusion. It diverges. That's it for comparison test and limit comparison test. Any question? Do we have any question? So you could have sum k from 1 to infinity, 3 over k square root of k plus 6, and it says limit comparison test. So ak is 3 over k square root of k plus 6. You build your bk taking all the highest powers of k. 3 is there. K to the power 1 plus 1 half. So that's k to the power 1 plus 1 half. 1 here, 1 half from that inside. So that's 3 over k to the 3 halves. You can actually leave the 3 out. It doesn't matter. It only changes is the limit you get in the end. So these are positive, right, which is fine. And so limit as k goes to infinity of ak over bk equals limit as k goes to infinity of k to the power 3 halves over k square root of k plus 6. And this is 1 because k to the 3 halves and k to the 3 halves cancel. Therefore, both series converge or diverge simultaneously. Sum 3 over k root k plus 6 and sum of 3 over k to the 3 halves converge or diverge simultaneously. But sum of 3 over k to the 3 halves is nothing but 3 sum of 1 over k to the 3 halves. And this converges. P series with P equals 3 halves larger than 1. Thus, the original sum 3 over k square root of k plus 6 converges. Now the next topic you had there was alternating series. And that is sum from 1 to infinity, -1 to the power n, Vn, with Bn positive. And we have shown that the remainder, Rn in absolute value, is less than or equal to Bn plus 1. And this is what is used when you want to estimate the remainder. When you're answering the question for alternating series, you want to show that it converges, you need to have 1. You're going to get your Bn defined to be positive. You need to show that Bn is decreasing or non-increasing if you want. And you need to show 3 that the limit of Bn equals 0. You don't just declare that it is decreasing, you show that it is decreasing. Now, the first problem on this is sum k from 1, sum k from 2 to infinity of 4 times -1 to the k over k times natural log of k squared. This is one of the problems that you had on your homework. And I think we also solved a similar problem in class last time. So in this problem, bk is 4 over k natural log of k squared. We never take the -1 to the power k into the bk. And so this is positive, obvious reasons. The natural log of k squared is positive. K is positive. 4 over a positive number is a positive number. And then you need to show me that this thing is decreasing. You don't want to take a derivative. Find another way to show that it is decreasing. You don't just write down that it's decreasing and it makes it decreasing. So either you learn how to use the derivatives or you find a way to show that. Now, bk is f of k equals 4 over k natural log of k squared. And I'm going to take the derivative to show that it's negative. So this is -4 times. And this, I'm taking this derivative as the derivative of 1 over f, which is negative derivative of f over f squared. That's a formula that you use in Calc 2. So the derivative of 1 over f, it's negative f prime over f squared. So 4, I just keep that 4 out, negative, and then I take the derivative of k natural log of k squared. And the derivative of k natural log of k squared, that's a product rule. So you use the product rule to take that derivative. That is going to be natural log of k squared plus k times 2 natural log of k times 1 over k. And that will be divided by k natural log of k squared, all of this squared. And this is minus 4. And then here you have things that cancel. And so you have natural log of k squared plus 2 natural log of k over k natural log of k squared, and all of that squared. Now, the bottom is positive with k larger than 2. Natural log of k is positive, so this is also positive. Everything here is positive, and the negative sign here makes this negative. And that implies that bk is decreasing. Moreover, limit as k goes to infinity of bk equals limit as k goes to infinity of 4 over k natural log of k squared. Natural log of infinity is infinity. Infinity squared is infinity times infinity. It's infinity. 4 over infinity is 0. So we have all the rules. Therefore, sum k from 2 to infinity, 4 negative 1 to the k over k natural log of k squared converges. That's how we use the alternating series to show this. And if any of the three things is not satisfied, then you cannot use the alternating series to decide. If the limit is not 0, then you can conclude using the divergence test that the series diverges. Questions? Questions? The other question is about the number of terms to estimate the remainder. Okay, so this is the sum k from 1 to this, and the question is how many terms are needed for a remainder less than 10 to the minus 5. Okay, so how many terms of this series are needed for the remainder to be less than 10 to the minus 5? And that is answered by what I wrote at the beginning here. Absolute value of Rn is less than or equal to Bn plus 1. So in this case, first of all, you need to identify the terms. So Bk here is 1 over k to the power 5. So that's Bk. And this is an alternating series. That's important. It's not alternating series, that formula doesn't work. Thus, absolute value of Rn is less than Bn plus 1, which in this case is 1 over n plus 1 to the power 5. And you want this to be less than 10 to negative 5 to be sure that your remainder is less than 10 to minus 5. and that gives you n plus 1 to the power 5 is larger than 10 to the power 5. So n plus 1 is strictly larger than 10, from which you get n is strictly larger than 9. If n is strictly larger than 9, then you need at least 10. So that's what you need for that part kind of question. And then you have the question on absolute convergence. And you have a sum, an, is absolutely convergent. If and only if the sum absolute value of an is convergent. That's it. And that's where the question starts. You first show if this doesn't work, then you go to the next step. You don't start by showing that it's conditionally convergent before going to absolute convergence. You look for absolute convergence. If it's not the case, then you look for others. Now, when you get that, let's say we have a question sum, okay, from 1 to infinity. Negative 1 to the k plus 1 over k to the 12/5. And that's about absolute convergence. So we will go ahead and we say sum k from 1 to infinity of absolute value of negative 1 to the k plus 1 over k to the 12/5. This is sum k from 1 to infinity. Absolute value of negative 1 to the k plus 1 is 1. So that's over k to the 12/5. And now this sum, 1 over k to the 12/5, this is a p series. It converges. P equal 12/5. This is larger than 1. So it converges. Therefore, the series is absolutely convergent. There's nothing else to do there, and no need to write anything else to explain. Now, if I get this one, over k to the power 1/2, then, and the question is also about absolute convergence, conditional convergent, or divergent. Sum of absolute value of negative 1 to the k over k to the 1/2, k from 1 to infinity. This is sum k from 1 to infinity, 1 over k to the 1/2, and this diverges as p series, p equal 1/2 less than 1. So this thing doesn't converge absolutely because the sum of absolute values diverges. Now we want to see if it converges conditionally. Why? Because we already found out that it doesn't converge absolutely. Now, if we take bk equal 1 over k to the 1/2, this is positive. Bk is f of k equal 1 over k to 1/2, and you take the derivative f prime of k, it's minus, the derivative of this is minus 1/2 over k minus 3/2. Sorry, minus 1/2 over k to the 3/2. And that derivative is negative. So bk is decreasing, and limit of bk equals 0. 1 over k squared has limit 0. Therefore, this series converges conditionally. Why conditionally? Because it doesn't converge absolutely, and we just figure with these three conditions that it converges as alternating series. Therefore, it converges conditionally. Questions? Now, after this question, you have questions on power series. That was 4, 3, 4. Right. Taylor polynomials. An approximation. And the Taylor polynomial was Pn of x equals f of a plus f prime of a times x minus a plus second derivative at a over 2 x minus a squared, and so on to the nth derivative at a over n factorial x minus a to the n, with remainder absolute value of Rn of x less than or equal to f n plus 1 at c absolute value over n plus 1 factorial absolute value of x minus a to the power n plus 1. That's what this was. Any question could be, use linear Taylor polynomial to approximate square root of 1.1 For example, in this case, f of x is square root of x. A is 1, which is the number that is closest there. Now you can easily find the value of the function, right? And so you're gonna get f of a, that's f of 1, that's square root of 1, that's 1. F prime of x is 1 over 2 square root of x. A is 1, so f prime of 1 is 1 over 2 square root of 1, so 1/2. And then second derivative, you can take derivative here, it's going to be minus 1 over 4 x to the power 3/2. And with a equal 1, okay, you can just we use c here. So absolute value of f double prime of c is nothing but 1 over 4 c to the power 3/2. The polynomial linear means first order. So the linear polynomial here would be p1 of x equals f of a plus f prime of a times x minus a, which is f of a 1, f prime of a 1/2, x minus a, and a is 1. So that's p1 of x. And p1 of 1.1, that's the estimation, is 1 plus 1/2, 1.1 minus 1, which is 1 plus 1/2 of 0.1. Which is 1.05. And the remainder, absolute value of R1 of x is less than or equal to 1 over 4c to the power 3/2. This is absolute value of the second derivative at c, which is what I computed here. That goes here, divided by n is 1, so n plus 1 is 2, factorial 2 is 2, times the absolute value of x minus 1 squared. And now we need to find a bound on this. Now, this is 1 over 8 c to the power 3/2. So times, I can actually remove the absolute value because the square doesn't matter. For the square, doesn't matter whether you put the absolute values or not. So this is what you get. And you need to find an upper bound on this. And c, we say c is between a and x. A is 1, x is 1.1. So c is between 1 and 1.1. And the function 1 over c to the power 3/2 is decreasing. Therefore, the largest value of this here is going to be at c equal 1. So we can plug in c equal 1 here, we'll have the largest value of it. So this thing is less than or equal to 1/8 times x minus 1 squared, with now x equal 1.1. You get that absolute value of R1 of 1.1 less than or equal to 1/8 times 1.1 minus 1 squared, which is 1/8 times 0.1 squared, 0.01 over 8. So the maximal error you're making on this thing is 0.01 over 8. And that is for Taylor polynomials what we do. Now the next thing with these power series was mostly the power series based on 1 over 1 minus x equals sum k from 0 to infinity x to the power k. This is mostly what I gave you on that homework. Power series that are related to this. That will be the last question here. So, the last topic. So that's about 6 topics, as you can see on this review, that are on your test. You need to use this review to prepare for your test. All the topics are on it. Now, question here is, find the function represented by the following series and find the interval of convergence. This is true for absolute value of x really less than 1. So 1, find the function and interval of convergence. And the first one was sum k from 0 to infinity x squared plus 1 over 3 to the power k. And so by this rule, this is equal to 1 over 1 minus x squared plus 1 over 3, when absolute value of x squared plus 1 over 3 is less than 1. So the function you get, and the 3 goes up, you got 3 minus 1, that is 2 minus x squared, so that's f of x. And then here, you solve this, because x squared plus 1 over 3 is always positive. That means x squared plus 1 over 3 is less than 1, which means x squared plus 1 is less than 3, which means x squared less than 2, which means negative root 2 less than x less than root 2, and there's nothing else to do. There's no need to plug in anything for these questions, because the interval of convergence already given to you. All you need to do is plug the corresponding function in there and solve to get the interval. Any questions? Next question was of the form sum k from 0 to infinity 6 e to negative 6x 6kx, sorry. And this is typically sum k from 0 to infinity if you understand the rules of powers. So this is negative 6x raised to the power k. And thus that is 6 over 1 minus e to negative 6x, when absolute value of e to negative 6x is less than 1. And nothing else to do. All you got to do is use that to find the interval. Absolute value, that it's not necessary because e to negative 6x is always positive. And now here, the function exponential is strictly increasing. So you can apply natural log to both sides here. So you get negative 6x less than natural log of 1 is 0. And that gives you x strictly larger than 0. So that's the interval of convergence, 0 to infinity. And there is nothing else to provide there as work. Any questions? So the other question was like asking you to do backwards what we just did. Find the power series centered at 0. And then interval of convergence. Again, it's all same questions related to the sum of x to the power k. So this f of x is 1 over 1 minus x to the 8th. And that's it. It's sum k from 0 to infinity minus x to the 8th raised to the power k. And now if you want to remove this minus 1 here, you be careful. You need to use parentheses. Sum k from 0 to infinity, negative 1 to the k, x to the 8k. If you don't have those parentheses, you have a wrong answer. And you got absolute value of negative x to the 8th less than 1. This is what gives you the interval of convergence. And then there's no extra work to do for that because this is given to you for free by the lecture. And now here, you're going to get x to the 8th less than 1. And for x to the 8th to be less than 1, you're going to have x squared less than 1. And that's going to give you negative 1 less than x less than 1. That's the interval of convergence and nothing else to do. And the last guy was radius of convergence. An interval of convergence. And let's say here I'm going to give you sum k from 1 to infinity, 1 over k times x minus 2 over 9 to the power k. Then you're going to have to find AK. And AK is all the numbers except x minus a to the k. So that's 1 over k times 9 to the power k. That's AK. And the a here is 2 because you got x minus 2 to the power k. And you're going to get me AK plus 1. That's 1 over k plus 1 times 9 to the power k.
Can you move the paper a little bit to the left?
And so AK plus 1 over AK, that would be k times 9 to the k over k plus 1 times 9 to the k plus 1. And then you simplify this. 9 to the power k goes with the power k here. So you get k over 9 times k plus 1. And that gives you that the limit as k goes to infinity of absolute value of AK plus 1 over AK equals the limit when k goes to infinity of k over 9 times k plus 1, and that's 1/9. And that tells you that the radius of convergence is 1 over 1/9, which is 9. Now, if you go try something else, you might be stuck. Now, for the interval of convergence, you need to check the endpoints. Check the endpoints. The first one is x minus a equals negative r, which in this case is x minus 2 equals, and negative r is negative 9, and that means x equal negative 7. So that's the lower point of the interval. And then you plug that in, sum k from 1 to infinity, 1 over k times x minus 2 is negative 9, negative 9 over 9 to the power k, and that is sum k from 1 to infinity, negative 1 to the k over k. And you need to decide whether this thing converges or not. How do we decide for this? Nicholas? How do we decide for convergence in this case?
Would you use the divergence test?
What type of series is this?
Is it a P series?
No. Sydney?
Is it alternating?
Alternating series. BK is 1 over k positive. F of k equal 1 over k. F prime of k is minus 1 over k squared negative. So BK is decreasing. Limit of BK is limit of 1 over k, and that's 0. So it converges. Then we check the second point, x minus a equal r. In this case, that's x minus 2 equals 9, which is nothing but x equals 11. So that's the upper bound of the interval. Then we plug it in, sum, okay, from 1 to infinity of 1 over k. And then x minus 2 is 9 over 9 to the k. And this is sum, okay, from 1 to infinity, 1 over k. So how do we decide for this one? Anyone?
Isn't that a p series with p equaling 1?
It is, and therefore the conclusion is
That it diverges.
diverges. This is actually called the harmonic series. So this is divergent harmonic series. So the upper point diverges, we cannot include it. The lower point converges. So the interval of convergence is -7 included, 11 open, or -7 less than or equal to x strictly less than 11. These two notations mean the same thing. That's it. And those are the 7 questions or type of questions that you have on your test. Thank you for coming today. I'll see you next time.
Can you move the paper a little to the left?